When we started, it was really a physics game. It was only physicists like me coming from the university trying to solve these problems. But now, actually, especially on the supply chain, we have very big semiconductor companies starting their own quantum programs, big foundry companies like Global Foundries, Applied Materials, and others. So this means that in addition to the physicists, there is now a whole crowd of well-trained engineers who know how to scale technology behind this. And this is what makes me so optimistic that we are going to execute holistically as an industry on these roadmaps.
One of the most exciting areas of technical development anywhere in the world at the moment is quantum tech. And amongst the most exciting aspects of quantum tech is quantum computing. Today, we are joined by the CEO of one of the leading quantum computing companies in Europe and indeed the world. We're joined by Jan Goetz of IQM, which is a company based in Finland. That they are listed on the Nasdaq, and they have a rare ability to actually ship and provide ready-made quantum computers. I'm joined by Jan today to talk about the technology, to talk about the company, and talk about the nature of the business generally. Jan, welcome to our podcast. And Jan, can I start with the impossible question, which is, in 1 minute, explain what quantum tech is, and particularly what quantum computing is?
Yeah, well, thanks a lot for having me. It's a pleasure. And quantum computing, as the name says, it is about computing. And ultimately, you need a machine that computes. So this is what we do. We build computers where you can program a problem in, you wait some time, and then you get the answer back. But now it also has the word quantum in it. So the way we build these machines is not on a transistor-based approach, like you have it in your normal laptop computer or smartphones, but we use the quantum version of it, which we call Qubit, so a quantum transistor. And they follow actually different rules of physics. And this means they can do certain things more powerful. So instead of being just 0 or 1, they can be in any superposition in between. And if you have many of them on a chip, they can be entangled, which means they share information. And this means they can run certain algorithms much, much more efficient than conventional computers. And it's not about a factor of 2 or 10 times faster. It's really exponentially faster. And this means that some problems can be solved in human timescales, let's say minutes or hours, where other computers, even the biggest supercomputers, would take millions of years. And these problems you find in actually all fields across industry. You find them in simulating molecules, for example, for drug discovery or material science. You find them in optimization problems for optimizing supply chains, traffic flow, financial portfolios and the like. And of course, also nowadays, everyone talks about AI. So you also find them in AI and quantum machine learning and the like. So it's a huge potential to unlock problems or the answers to problems where we know today we will never be able to solve them without quantum computers. And this is what it makes it so exciting. It's really opening the doors in a completely new world. And these doors would stay closed forever if we wouldn't build a quantum computer.
I mean, it seems to me that it solves problems that we hard to conceive even what they are, but the potential for advance across a huge range of fields in terms of optimizing solutions of one form or another is quite extraordinary. Now, what do you find as a common misconception when you talk to people about the nature of quantum computing?
Yeah, many people think it's still maybe crazy science in the lab or even some kind of black magic because it's hard to understand. But the fact is, as you mentioned, we are building and shipping real computers into real data centers. So we are the company that has sold most on-premise computers into data centers and research institutions. We just announced another big deal where we integrate a quantum computer into a so-called AI factory. So what we do a lot is then when we ship the computer into the data center, we place it right next to the server racks full of GPUs and CPUs and memory, and then we connect them. So it is actually real and it's happening today. the quantum computers that we build, they work. You can program your algorithm in. The answer that you get out is correct. But the technology still needs to improve further to really unlock all these commercial applications that already kind of hinted on. So it is, in the end, it's very similar to what happened in semiconductor industries, where we have been observing Moore's law, the doubling of transistors every other year. Something similar is happening in quantum, and we are just at the beginning. But the technology is working, it's real, it's out there. We are going to build bigger and bigger machines, and we are going to unlock then all these commercial use cases that I've been talking about.
I mean, coming into this area, it seems to me one of the crucial things to understand is that it is not science fiction, that this is not some speculative future technology. We have quantum computers and they work. The question is the scale and the commercial viability of them. There are various parameters you can measure quantum computing by, the number of qubits and the error rate and so on. Give me a sense of what you think the key parameters are for quantum computing and the thresholds that may be achieved, which would unlock various use cases.
Yeah, so we are still very early on this journey, as mentioned, and people talk really about chip parameters. This would be as if you would still talk about the number of transistors in your smartphone. We are talking about the number of qubits on the chip. And obviously, in computer industry, nobody talks anymore about how many transistors are on the chip. So this is the transition we need to achieve as an industry, is steering away from these discussions of how many qubits do you have, how do they work, what's the quality, and we need to steer it to the discussion, what are the use cases that we can actually unlock, and what is the time to get there, and maybe what's the investment amounts to get there, and what's the impact then that these use cases have. But still, it is very early. It's very much research driven. Also in our organization, we are a spin out from the university labs, as many other quantum computing companies. We have a strong, very big R&D team, and that's rightfully so. But I think the discussions, they need to be brought to a higher level, away from the qubit parameters, to the use cases and to the impact on industry that this technology will have.
So if I'm looking across a number of offerings in terms of quantum computing, and there are all sorts of different models, some using cryogenics, some using other forms of technology, what am I looking for in terms of the capability of the systems? What are the meaningful outputs that I can have?
Yeah, so many organizations today, they start engaging with quantum computing because also for them, it's a journey. So not only for us building the technology, it's a journey also for the end users. And I think many have experienced this now in AI, that is not just you switch it on and suddenly it works and your organization is full of AI. But you need to get the people behind it. People need to trust and believe in the technology. And you need to get your processes right. Also from a regulatory framework, if you work in such industries. And this is what's happening now in quantum. Organizations are getting quantum ready. And this means they need to build up, of course, the know-how inside, and they need to test and validate it on real machines. And this is where we come in into the equation, is we provide companies and other organizations this opportunity to work on real machines, either through the cloud. That's the lowest barrier entry. Obviously, you just sign up and we are in AWS or through our own cloud. Or, of course, then through a more kind of directly deployed installation. The interesting fact also here is that in deep tech, often it starts with government deals. They are the early adopters and they take away some of the risk. But actually, what's happening now in quantum is that out of the last deals, actually, we announced just 2 deals to enterprise customers. So companies not only buying cloud time, but actually investing in the hardware, buying the real computers. This was a space tech company in Poland and a automotive testing company in Japan, 2 very established businesses, and they believe in the technology and that it makes sense to own the hardware and really train their employees on the actual hardware. So this is where we are also in terms of industry adoption, is that people get moving, people get started, and they kind of engage and educate themselves and their organizations with this new technology.
Now, I want to get back to the tech and particularly how you're engaging with your customers in a way, but can I just go back to your own personal journey on this, which I think is fascinating, because you're a researcher, I think you're a physicist by background. At what point did you think you wanted to go into business, and what prompted that?
Yeah, it's a good question. And I never thought about it myself, actually. So my goal was to become a professor. And I was on this journey. I did my PhD, I did a postdoc. I ended up then in Finland working there at Aalto University, building up a lab, building these prototype quantum computers. And what usually happens in academia is your contract is only for 2 years and you move on to the next place. And I was talking to my professor saying, hey, my contract is about to end and I will look for something else elsewhere. That's the normal part of the business in academia. And then he said, well, why don't you stay here and we build a company together, a spin out from the labs? And I was like, okay, I don't know what that means, but it sounds exciting. And in the beginning, really, I thought this was just a research project on steroids. So instead of raising hundreds of thousands from the scientific funding agencies, we were raising millions or tens of millions from private or venture capital investors. I was a quantum physicist. I didn't have any business background. Obviously, my goal was to become a professor. So I was jumping into the cold water, and we learned most of the things on the fly, or then, of course, we hired the right people. And I think still deep inside, I'm motivated by this challenge to build a machine that no one has built before, which is a very technical task. But I don't build it myself. I empower and enable others to build it by doing the work that I do, which is talking to investors, talking to media and others to create an environment with the company and with the funding that we get and the infrastructure that we build so that all of these great engineers and scientists that we have, that they can do a proper job and build a really strong quantum computer.
And what was the hardest transition moving from a world of academia to the commercial world?
Well, it's a constant transformation. So if you start the company, the work is maybe not so different from an early career researcher where you build up a lab, you hire your first PhD students. And when you start the company, at least in our case, we also needed to build a lab. We needed to hire the first employees. But then, of course, very soon you realize, okay, there's much more to it, right? You need to think about legal, you need to think about product, maybe commercialization and marketing, and at some point, IP and all of these topics. So it's much more holistic. And this is what's so exciting about it. And but you as a person, you have to transform yourself all the time from a very early entrepreneurial founder to a founder that helps the company scale. Now we went public, which of course, again, is a very different beast. And you need to talk again to different type of investors. And you have very different obligations in terms of financial reporting and what you're allowed to say and not to say. So as a founder, throughout these, now it was 7 years in our case, from spin out to going public, you have to transform yourself all the time. And I think that's a challenge for many founders. And it's a privilege to kind of still be in this position and being allowed to lead this really amazing business.
And you talked about providing the space to allow your brilliant engineers to do their work. Do you not find yourself personally drawn into either the science or the engineering that is, after all, your background?
Well, I try to stay connected to the science and the technology that they build, but I don't do it myself anymore. And of course, also when I tell the story and I pitch what we do as a company, I need to understand the technology and I need to understand our roadmap and the plans, but I don't have to develop all of this. And for me, at least, this feels very comfortable. It's a different challenge. Executing this roadmap is a huge challenge. It's a very ambitious roadmap that we have. But of course, you also need to have someone who is building the business, pitching the business to investors. And it turns out that this is a skill that I have, and I see myself very much as a servant leader here. And I'm leading, I'm serving the company, and I'm serving our people that are building the technology.
And I'm always interested at the beginning of a startup. There you are with some of your colleagues proposing to embark upon this commercial development. How did you divide the roles? You've taken one particular public-facing role. Others of your colleagues have adopted different roles. How was that decided?
Yeah, of course, everyone has strengths and also maybe then weaker points. And for me, it was clear that I'm quite good, I think, at explaining stories that we're doing. I've been doing a lot of scientific presentations when I was still on the academic side. I've been writing a lot of proposals, as said, for the scientific and academic funding agencies. So it was clear that this is something I can do. I'm not per se maybe the best manager from this perspective, kind of managing the day-to-day operations. So then we had other people. So for example, one of our co-founders who has been working more in project management after the PhD, he has been taking a more operational role. Another co-founder has taken then this CTO role of pushing the technology. So it was really, I think, playing to everyone's strengths, and since then we have been running like this.
Now, go back to the rollout of this technology. You are producing quantum computers. They're still somewhat at the assessment stage, but you're selling them, customers are engaging with them. Another impossible question, how do you see the timeline for the adoption of quantum computing over the next few years?
Yeah, so as mentioned, it's very similar to semiconductors in the way that underneath there is a processor roadmap. And every other year or so, we tape out and produce a new and more powerful quantum processor. We are running our own design tool for this, a chip design tool. We are running our own chip factory and then the assembly line to build the computers. This year, we are still delivering 150 qubits or qubit systems to customers. And every year there will be more qubits on the chip and higher quality on qubits on the chip. And we will implement error correction, which is crucial for this technology. So to correct for the errors that are still happening on the chip. And we do see that over the next years, we are getting closer and closer to use cases, but it is not so black and white that all of a sudden quantum computing is working and you can run every algorithm. But it's very similar to what happened in the GPU sector. If you look at the graphics processing units, the GPUs, they have been developed for graphics applications, video gaming and the like. This was the first use cases. And then over the years, they have been becoming more and more powerful. And as they became more powerful, more use cases have unlocked in maybe crypto mining, molecular simulations. Now it's all about AI and LLM trainings. And this is how we see it also in quantum computing. Over the years, the processors get more powerful and more use cases get unlocked. And maybe we start with the first ones, probably in molecular simulations, simulating quantum systems with a quantum computer. And then at some point, we add optimization problems to the mix. We add AI problems to the mix, maybe cybersecurity problems to the mix. And so it's not so that all of a sudden there will be a full adoption, but it is an adoption curve. And we are still at the very beginning. I think there's still a lot to be done, but also a lot of potential to unlock.
And in terms of the incremental progress you make with your technology, are there any limits? You talk about Moore's law, and Moore's law has been in place for 40, 50 years. Every time we think we're getting to the threshold of the limit, then new technologies emerge one from another. Are there any theoretical limits, or can we expect that kind of progress in terms of your technology for the foreseeable future?
I think from a scientific perspective, yeah, there are no limits at the moment that would hinder us from building these fault-tolerant universal quantum computers. However, technology, of course, needs to be developed, and technology needs to play to its strengths. And the way we see it is that not quantum computing replacing all other compute modalities, but more working together hand in hand and really unlocking synergies. And you have to think about this more like an orchestra of computers. And in an orchestra, you have different instruments, and each instrument plays the part that it's best at. And that's the same that's happening right now in data centers. You have different compute modalities, and every compute modality is doing the task that it's best at. GPUs, for example, handling a lot of parallel data, and CPUs doing a lot of the orchestration work, and then quantum computers are added to the mix, and they can work on these really, really hard, mathematically complex problems. And all together, they solve the outstanding problem. And there's an orchestration layer on the software on top of this. It brings back the answer. So this is how we see it. It's really a hybrid way of compute, where different compute modalities work together rather than quantum computing replacing all of our data centers and all of our current compute.
And as I understand, another part of the orchestra, and this is the development of the mathematical algorithms, which can make a huge amount of difference. I think just this year there have been at least 3 very significant papers in various aspects of quantum computing, because the area is so theoretically based, and that's maybe something which doesn't really apply to traditional computing quite as much, at least outside the realm of AI. Is that right to think that the whole area is significantly dependent upon very abstract mathematical concepts.
Yeah, and I think also in the conventional computer industries, of course, the algorithms have been improving over the years quite a lot. And I think the interesting thing here is that, of course, we will make progress on the hardware side, and we will build bigger and bigger computers, and we have a very detailed engineering roadmap there. On the algorithm side, it's a little bit different. You cannot really plan this so much from an engineering perspective. You cannot say in 2 years I will have a 10 times better algorithm. But it's more like these things just happen. Someone has this genius moment and they come up with a better algorithm. And I think, yeah, a good example is one use case in quantum computing is the code breaking, which of course makes it very interesting also from a strategic and geopolitical perspective. And here, when the original algorithm was created in the mid-90s by Peter Shaw, people thought that you would need 1 billion of qubits on a chip to run it and to break RSA 2048, which is our current encryption scheme. And then over the years, this algorithm, all of a sudden, it was improved and the number went down to 20 million qubits. And then it went down maybe to 1 million qubits. And yeah, now recently there were even more papers bringing it down to below 100,000 qubits. And these are step functions. And that's so exciting about it. You can really gain an order of magnitude there, but it's also unforeseeable step functions. And nobody knows if tomorrow someone will publish a paper again. And this makes it so exciting. So the gap is closing. It's closing very steadily on the hardware side because it's very engineering driven and there are long-term roadmaps, but it's closing in step functions then from the algorithm side. And that makes it so interesting and also unpredictable.
We exactly, and there's a serendipity about use cases which suddenly emerge, which you referred to before. But there seems to me a serendipity about the fundamental mathematics developing and completely transforming the capability of the sector. And if you're looking as a third party, either as an investor or as a customer, to engage in quantum computing, and you're looking at the current capability, you need to be aware about the huge potential for, as you say, the step changes which may occur, not just with the underlying technology, but because the theoretical mathematics behind it may step forward like that. It seems to be an area which you need to keep a very close watch on. In terms of synergies, you've talked about AI. I think it's fascinating to look at the interaction between AI and quantum. There are all sorts of ways they're wrapped around each other. AI being used to design quantum machines in time, quantum providing kind of back end to AI technology and so on. How do you see the interrelation between AI and quantum, both at present and going forward?
Yeah, exactly like this. So these two technologies, they will benefit each other in both directions. And this is what it makes it so exciting. And this is one of the reasons why we deploy our systems into the leading data centers around the world, because they're already running their GPU clusters. So they're server racks full of GPUs. And then we bring our quantum computer there, we install it in the very same floor, data center floor, right next to the GPUs, and we connect them. And then they can start working together. And on the one hand side, as you said, we can use AI to, for example, design better chips. We can also use AI to, for example, optimize the tune-up and calibration of our computers. We can also use GPUs there to do real-time decoding of error correction. So there are several use cases where quantum computers benefit from AI, but then also the other way around. So there's a whole field of quantum machine learning and applying quantum computers to machine learning algorithms. The whole topic of synthetic data generation, for example, to train more efficient models is another one. So we do see that AI will also benefit from quantum computing. And this is why I think also the big names in AI are looking into it. And you see that companies like NVIDIA or AMD have very strong quantum programs, not where building their own quantum computers, but integrating and connecting their technology to the quantum technology.
I want to talk a little bit about the challenges facing the sector, exciting as it is. First of all, what you see as the key technical challenges, which particularly your company faces.
Yeah, as I said, it's really about scaling. To unlock this Moore's law behavior for quantum, we need to get from these hundreds of qubits where we are to thousands, maybe, or not maybe, but then millions of qubits at some point. And this means the technology needs to evolve over time. We don't need scientific kind of breakthrough still, that we say somewhere there's like a black spot in our roadmap and we don't know how to solve it, but it's hard engineering tasks there. Just to give you one example, the way we currently connect the processors to the outside world is with very, very ordinary cables, coaxial cables, and they are quite microscopic in size. And it's okay to have hundreds of those cables connected to the chip. That still works. But if you think about millions, that's not going to be through these cables for many reasons, right? Nobody is going to screw 100 million cables to a processor, and also if you think about the cost factor and all of this. So we need to get rid of the cables and replace them by kind of on-chip technologies. And this is what we are working on in our roadmap. And there are several other kind of examples like this, where we just need to do proper engineering in order to replace the current solution on how to build the machine to a solution that's then more scalable going forward. And there's lots of value that's being unlocked. And what makes me very positive here is that when we started, it was really a physics game. It was only physicists like me coming from the university trying to solve these problems. But now, actually, especially on the supply chain, we have very big semiconductor companies starting their own quantum programs, big foundry companies like Global Foundries, Applied Materials, and others. So this means that in addition to the physicists, there is now a whole crowd of well-trained engineers who know how to scale technology behind this. And this is what makes me so optimistic that we are going to execute holistically as an industry on these roadmaps.
Well, that brings me very nicely on to my next question, which are the other challenges facing the business, but particularly the recruitment of talent, because it seems to me a really interesting set of businesses in quantum, because you need some incredibly sophisticated theoretical physicists to understand the quantum technology, but you also need this tier of engineers, because the problem you explained about delivering the output using coaxial cable is a classic, albeit a very complicated engineering problem, and so on. How do you see the range of talent that you need? And do you see that as a pinch point? Are you able to recruit the people you need? Is there a global talent base? How do you view the talent issue?
Yeah, of course, that's a challenge globally, and there is only a limited amount of people graduating in nowadays it's often called quantum engineering. Good news is that many universities are ramping up their quantum engineering programs, but of course it takes time to educate new students. It doesn't happen overnight. And for a company like us, we are very much vertically integrated. We have a lot of system know-how, but this also means, yeah, we need chip designers, we need people going to the clean room, working there. We need people doing the system engineering, people working on the software side, compilers and the like. So we need a whole spectrum of engineers and scientists, but we also ultimately we need people who know how to market our products, how to also on the product side, product development, and sales, people who understand how to sell these very complicated machines. So it's really across the stack where we need special talent. The good news is actually we are operating out of Europe, and in Europe we do have a very high density of talent. And this is one of the key advantages that also we have, where in the US the competition is quite fierce, since also all the big tech names are working on quantum computing. In Europe, I think we have a very strong standing, and we have been able to recruit really a world-class team, not only in terms of team size, also in terms of quality. And we are bringing people also here back to Europe. People are relocating to join this exciting project from the US, from the APEC region. And so from this perspective, I think one of our key advantages is the super strong team that we have. But of course, as the industry scales, this problem will not go away. We are just kind of about to get started. And if the industry really scales and people are expecting it to scale, there will be a very, very fierce competition around talent.
And I wonder if you could just briefly address three other external factors, which may be commercial challenges. First of all, the investment community and the extent to which people are ready to invest capital in this area. Secondly, the consumer, your potential customer base, and the extent to businesses are ready to take on products at this stage, and the kind of relationships you're having with your customers. And thirdly, the approach of governments to this, both in terms of creating the environment which will allow businesses to expand, but also the potential regulatory restraints. You refer to one use case, the decryption, which is a very startling one, which gives rise to concerns. But it is an area of export controls and at least putative regulatory controls. So sorry to ask you a very elongated question, but perhaps if you could deal with those in turn, the investment community, the customer relations and government.
Yeah. And of course, it's also somewhat interlinked, all of this. But on the investment community to start with, of course, when we kicked off our seed funding round in 2018, quantum was really, really new to all kinds of investors. And we had to educate the venture capital community. And over the years, people have become more and more educated. And now, of course, we have several companies, pure play quantum computing companies that already went public. And we have big institutional names like BlackRock and others and engaging. So it has also been a journey there on the investment community. And the good news is that people are still investing across let's say, the stack. Just this, let's say, first half of the year, we have seen many private funding rounds north of $100 million, for example, from VCs and others. At the same time, we have seen a number of companies going public. So we see actually good investment behavior across the different kind of investment classes there. And it's similar, I think, on the business and the customers. Also there, I mentioned already, it's a journey. There are early adopters who have been already on the journey longer. And we see also different levels of engagement. We see some companies who really, really invest heavily. One example is Novo Nordisk in Denmark. They're investing hundreds of millions into their quantum center there. And others are really saying, okay, we build up our team, and then let's really work on the use cases first until we make bigger investments later. So it's also there a spectrum of people who are a bit more risk-taking and others who are following rather. And I think that's good. We need also, of course, a constant flow of customers coming in. If hundreds companies would come today and say order something from you, of course, also would be challenging for us as we need to grow as an organization as well. And the role of the government, the third part of the question, is of course to consider the technology from this geostrategic angle on the one hand side, which is the code breaking and the dual use cases, but of course also the economic impact on the whole economy. And here, what we have seen is mainly two things. On the one hand side, governments investing into companies, especially in Europe. This has always been more a thing. And in our case, we have the European Commission, the Finnish government, the German government on the cap table. And then in the US, this has recently become a thing as well, like the recent announcements from the White House taking equity stakes into companies. So this is one thing. But then on the other hand, it's really the procurement, public procurement of computers, which I think is the best way for a government to support a new industry, because it defines the industry, to define products, and it creates revenues, and these revenues can then be used, of course, to attract more private investments, but also it brings the companies to a higher maturity level with their business, because we need to sign contracts, we need to follow the contracts, deliver, and all of this. It's much more efficient for a government to go through a public procuring route rather than just providing research grants. So this is something that we have been welcoming a lot, initiatives around the world where governments have been supporting the procurement of quantum computers into data centers.
And the UK government in particular, I think, has a investment fund of actually up to £2 billion to develop the quantum technology sector in this area, with a particular ambition to produce a viable, commercially viable quantum computing system in the UK. I think you may be a front runner in that as well, but a very interesting area. So look, we're nearly out of time. I just want to ask you one or two questions about the market in there. Obviously, the United States is enormously advanced in this area, although Europe is punching its weight. How does IQM compete with the US hyperscalers like IBM, Google, and AWS in this area?
Yeah, of course. Ultimately, it's a global competition. At least, I mean, it's an industry that is already export regulated, but other than that, it's a global competition. So all the, let's say, Western tech nations are interested in quantum computing, which obviously contains the US and Europe, but then also in Asia, in particular countries like Japan, Korea, Taiwan, Singapore are very, very active. And we welcome the competition. Obviously, if there are big names saying, hey, this is a technology we invest in because we see a huge potential of this technology, of course, it gives a certain quality stamp to the technology itself, rather than if they would be saying, oh, this is all crap and it doesn't work anyways. So overall, I think this is a good thing. And the way we see it is not a winner takes it all game. In computing, usually you have a few dominant players. And this is really our ambition level, is to be one of these globally leading players. And in particular, we are leading in one sector, which is the deployment of quantum computers into data centers. This is one part of the business, and we just announced a very big deal again, where we integrate into an AI factory a quantum computer, so the machine will be physically there. And the other part, obviously, is the cloud business, and this is something that we are ramping up as we speak. But overall, I think if you have a competitive product, you can compete even with very strong tech brands. And we have been selling, even in the US, we have been selling to Oak Ridge National Labs, which is one of the biggest supercomputing facilities in the world, actually. And we were the first quantum computer there that they bought, which shows that if you have a product that is competitive in the market, you can compete even in the markets which are the most competitive markets, like in the US. So we are very, very optimistic, and we are believing strongly in our technology, our approach, and we are welcoming the competition.
So let me just finish with a little bit of being future facing. Over the next, say, 3 to 5 years, what are the milestones that we should be looking out for? And if we were to have this conversation in 2030, say in 4 years' time, with IQM, what would you be saying then that you're not saying now?
Yeah, for companies like ours, I think it's really the execution of the roadmap, which means developing the technology towards commercially viable computers and being able to produce them and deliver them. It's also not only about building one machine kind of in a science lab. If you want to scale the business, you need to be able to scale, also making copies of these machines, and hopefully many, many copies of these machines. So I think these are the points to look out for, how companies are executing their roadmaps and how they are able to productize and commercialize this technology. And then, of course, on the adoption side, it's really, yeah, which use cases are getting closer to reality, which companies are engaging, and how are they investing into quantum computing. And of course, the goal is that, let's say in the 2030s, when we are having such a discussion, is that the use cases, and maybe not all of them, but at least the first ones, are already running on real quantum computers. And we have shown that it is possible to build the technology not only at scale, but also at a commercially viable scale, so that there's return on investment for the end users.
Well, Jan, it's been tremendously exciting speaking to someone at the cutting edge of such an exciting technology. If people listening to this podcast are interested and wish to engage in the sector, what should they do?
So we have actually a free online platform which is called IQM Academy. So if you're interested in how a quantum computer actually works, and get convinced that it's not black magic, but it's running there for sure, go and check out. Of course, others have similar offers, but I think the best way is to really get engaged and maybe even start playing around with a real quantum computer. It is possible, and they are out there in the cloud, and you can sign up for free. So I think this is the best thing, that if you can say, hey, I did a few lines of codes on a real quantum computer and executed it, I think it's a really pleasant experience.
Well, who could resist the temptation of doing that? Jan, thank you so much for your time today. That's been absolutely fascinating. And I wish you really well for your business, which is, as I say, so exciting. Thank you again.
Thank you.